Alright, let's start off by looking at an atom. So an atom has a dense, positively charged region in the center called the nucleus. Very, very small compared to the rest of the atom. Then surrounding the nucleus in a three-dimensional area is what we call the electron cloud. And the electron cloud is just where the electrons are found. However, if we want to get more detailed about those electrons, which we do want to get more detailed about those electrons, we couldn't just describe them as being in a cloud, because they're not just randomly out there in the cloud. Rather, they're in certain specific orbitals or regions of the electron cloud. So back in like freshman science, or even the last unit, we would have described like if this was nitrogen. We would have said, hey, nitrogen, it's got 7 protons in that nucleus, and it's just got 7 electrons out here in this guy. We went so far as last unit to say, okay, there's 2 electrons in the first row, and then there's 5 electrons in the second row, but that was as detailed as we got. We need a more specific way to describe where those electrons are, rather than just saying, hey, there's 7 of them. We need to specify a kind of a map of where all 7 electrons are found. So here's a periodic table that we can use as our guide as we talk about this. So I'm going to go ahead and shrink that up, get your periodic table out too. And if we look at nitrogen, for example, so nitrogen does have 7 electrons. You've seen in the previous video all the quantum numbers that we use to describe the electron. Let's give it some more detail than that. So the first way that we can specify those electrons for nitrogen is what's called the orbital notation. With the orbital notation, we use just the sublevels in the orbitals. So for example, we would start with the 1s, and then after 1s comes 2s, and after 2s comes 2p. And there is 3 different versions of the 2p. So that's 3 different orbitals within the 2p sublevel. And after 2p would come 3s, and after 3s would come the 3p's. You notice how I'm drawing up a little bit higher. That's just because the amount of energy that the electron has increases as you go up. So the least amount of energy would be this guy, the highest amount of energy would be that guy. Which plays a role then when we talk about the Aufbau Principle, A-U-F-B-A-U, which says that electrons, when you fill these orbital notations in, you always start at the bottom, so you start at the lowest energy level and work your way up. So you'd never put an electron up here when there's still room down there, because that's higher energy than this guy. So let's do nitrogen. For electrons, we use up and down arrows to specify the spin direction. So we would put a up arrow and a down arrow. And those different arrows that just indicate different spin directions, that's the final quantum number. And so they would have the values of -half or +half. And as to which is which, doesn't really matter. Okay, we can keep filling these in. So after that one's filled, we go up to the next energy level. Go up and down. We now have 4 electrons, so we have 3 more to distribute. So if we put 1 right here, that's number 5. We've got 2 more, but let's pause right here and talk about the Huns Rule. So we've got the Aufbau Principle that we talked about, where we build up. Next is the Huns Rule. And the Huns Rule says that we don't add electrons together if there's still room. So you notice all 3 of these 2p's have the same amount of energy. And so we don't have to fill this one before we fill that one. In fact, since electrons are negative and they repel each other, we're not going to put the next electron right there. It's going to want to be by itself because it doesn't have to share a room. So it's going to come over here. And then the last electron is going to go right there. And another part of Huns' rule, not only do they not share the same orbital if they don't have to, but they all have to have the same spin direction. So I didn't go up, down, up, or up, down, down. I went up, up, up. I could have also gone down, down, down. As long as all 3 are pointing the same direction, it's all good. So that right there then would be the orbital notation for nitrogen. It's got all 7 electrons. We've built it up. We followed the Huns rule. Everything is perfect. So let's try another one. Let's do chlorine. Chlorine has 17 electrons. And the nice thing is we don't need to erase what we already have. We can actually just follow the Aufbau principle and build up from here. So we're starting right there with 7 electrons. Looks like we need to add 10 more. So the next 10, now that we've filled in all of those with 1, hey, now we're going to have to start sharing. So we can go back, this is Huns' rule, come in, and then add those other electrons. The following electrons, the ones that come next, they have to point the same direction or opposite direction of the original ones. So they can't both be pointing up or they can't both be pointing down. And that right there is the Pauli exclusion principle. Pauli exclusion says that if they're occupying the same orbital, they have to have opposite spins. So we go up and down. So we put another one in there. Right now we've got 2, 4, 6, 8, and 10. We've got 7 more electrons. So we go up to the next energy level, which is 3s. We go up, that one's filled, so we put another one down. And it looks like we have 2, 4, 6, 8, 10, 12. We've got 5 more, so we're going to go up, 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 and then down, down. And right there, that's 17 electrons filled out. That would be chlorine. Alright, let's talk about a different method of writing electron configuration. So this one right here, the last one was orbital notation. This is called the electron configuration. With the electron configuration, it's a little less detailed, but a lot easier to write. So for example, nitrogen. Nitrogen we would write 1s2. So that means in the first energy level, in the s sublevel, there's 2 electrons. And then in the second energy level, in the s sublevel, there was also 2 electrons. After that came the 2p, and there was 3 electrons there. So that right there, that would be the electron configuration for nitrogen. We can see that nitrogen has 7 electrons. We've got 2, 4, and then 7 represented there. We can also do this for chlorine. Chlorine, which had 17 electrons. There was 2 in the 1s, 2 in the 2s, there was 6 in the 2p, there was 2 in the 3s, and then in the 3p there was 5. What you're going to notice is they all kind of start the same. They all start with the 1s, 2s, and they build their way up, and it just keeps getting bigger. So we can actually shorten this down by looking at the noble gases. So for example, neon. Neon's electron configuration is going to be 1s2, 2s2, 2p6. Now, since chlorine here started with the same thing as neon, we can actually shorten down chlorine, so instead we can write neon, and that means, hey, the electron configuration of neon followed by what comes after. So after the electron configuration for neon was that right there, so it's neon, 3s2, 3p5. And to do these, we just look at the noble gas that's right before the elements, like chlorine. If we go up one row, it'd be neon. If we want to do this for bromine, it would be, barium, it would be krypton. So let's do barium then. Barium, like I said, would be krypton. After krypton, which is right there, we would come down here, and that's going to be in the 5th row, the second element in, so it would be 5s2. Alright, now let's go ahead and chunk this periodic table into what we call blocks. And so if we separate it off into areas on the periodic table, what we'd find out is that all of these different areas, different blocks, end in a particular sublevel. So for example, these first 2 rows, which we call the S block, all end in the S sublevel. So that means all of these elements right here, if we had to write out their electron configuration, the last thing that we write would involve an S. And it also makes a difference what column and what row they're in. So this first column right here, they're all going to end in S1 because it's S. It's the first S. This row right here is the second S. They're all going to end in S2. And then the number in front, that tells us the energy level. So potassium then is going to be in the 4th row, so the 4th energy level. That means its last electron configuration is going to be 4s1. Strontium, which is in the 5th, would be 5s, and it's in the 2nd column, so it would be 5s2. The next block over, this is the D block. So all of these elements right here are going to end with the D sublevel. And then same thing if we go in order, so manganese is going to end in D1, 2, 3, 4, 5. Silver would end in D1, 2, 3, 4, 5, 6, 7, 8, 9, so D9. And then same thing with the rows, it does make a difference, however it's 1 off because of the energy. And so even though this is the 4th row right here, manganese is not going to end with 4D5, it's going to end with 3D5, so it's just 1 less. Silver, that's not going to be 5D, it's going to be 4D. Gold would be 5D, let's see, any of these down here, seaborgium, would end in 6D. And then this block up here is going to be the P. These are back to normal then, so right here this would be the second p, so all of those would end in 2p, 3p, 4p, and then the row numbers also make a difference, so sulfur, which is in the 1, 2, 3, 4th p, is going to end in 3p, 4. Bromine would end in 4p, 5. And then we come down to the bottom, and that is the F block. The F block, kind of like the D block, isn't exactly matched up with its rows. So remember, this row right here starts and continues on. So even though this guy is the 6th row, it's not going to be 6F. It would be 2 less. So this would be the 4F, and this would be the 5F. And same thing with the counting. This guy right here is going to be 4F, 1, 2, 3, 4, 5. This guy right here, or your uranium, is going to be 5F, 1, 2, 3, 4. So we could take advantage of this to make our lives a lot simpler then when we write our electron configurations. So let's go ahead and write our electron configuration for, we'll say, selenium. Okay, selenium is right here. So to write our electron configuration, we start at the beginning, Aufbau Principle, and we could fill in the electrons as we go through the blocks. So if we go through the first one, those would both be in the S, so that's 1S, and we added 2 electrons, 2. Next we come down here to the 2S block, fill that in with 2 electrons, so that would be 2S, 2. Then we come over here, that is the second P, we put 1, 2, 3, 4, 5, 6 electrons in there, so it would be 2P6. Next we came down to the 3S, we put 2 in, so 3S2, and we just keep following these lines across, adding our electrons until we get to the element we want. I'm going to come down here, and then once I get to scandium right there, I'm in the D. This is the 3D though, and I went 10 elements across, so it's 3D10, and then I have to go 1, 2, 3, 4 elements to get to selenium in the 4P, and so it would be 4P4. This also simplifies our lives with the noble gas configuration. So if we try and do the noble gas configuration for, let's say, iodine, right there. So iodine, its noble gas that we would use would be the one that comes before it, so that would be krypton. So we're going to start with krypton. And then we're just going to start off where krypton leaves off, which would be right down here. And so that row right there is the 5. So we're going to start with 5. We're going to start in the 5 in the S block. So it'd be 5S, and we're going to have to go 2 across that. And then after that, we're going to come to this row right here, which is the D block in the 5th row, so that would be the 4D. And we'd have to go 10 elements across there. And after that, we would go 1, 2, 3, 4, 5 elements over in the 5P. So 5P5. So there you go. There's the noble gas configuration for iodine. Alright, that's all I got to say about this. So that was kind of a crash course in electron configurations, but hopefully we've talked about most of this in class. Hopefully that was a good kind of review or refresher. Helps you figure out some things that you're still struggling with.